back to our big chart. So this is the same breakdown of all linear algebra problems, solutions to linear systems of equations and matrix equations and vector equations as we've seen before, except that now we're also bringing in the interpretation as a linear transformation problem. So we have T goes from V to W. It's an M by N matrix that represents T. So it has M rows and N columns. That means that the dimension of the domain V is N, and the dimension of the codomain W is M. So the question is a vector B in the range? Once you create the matrix, you can just augment it with B and ask, is that in the range? And the same thing as solving the equation AX equal to B for the matrix A. So now we have, for instance, if the columns of A are linearly independent on the left, the top half, then we know that T is 1 to 1, and that the columns will each have a pivot. So the solution will be unique when you augment with the zero vector, and so the null space will be just zero. You can also say that the nullity is equal to 0, and then you know that the rank is equal to n, since the nullity plus the rank have to add up to the dimension of V, which is n. That's true no matter what is true about the rows. But if the rows are linearly independent, then we know we're looking at a square matrix, because if they're both columns and rows are linearly independent, it has to be a square matrix. And that would also mean that the rank and is equal to M, which is also equal to N, and T is onto as well as 1 to 1. That describes the top row there, and the determinant of A is non-zero in the square matrix A. And you can find the inverse of A, so X is equal to A inverse B is the solution, and that's that's true whether B is equal to 0 or non-zero. Although if B is non-zero, X is also non-zero. If B is equal to 0, X has to be 0. Now, if the rows are linearly dependent, it's no longer square. In this case, the rank is still equal to n because of the columns being linearly independent, but that must be smaller than m. In other words, there must be more rows than there are columns, so we'll be seeing some extra rows possibly. And that means that there could be either one solution or no solutions if the vector b is non-zero. Because if the vector b is non-zero, you could have that row where there's a contradiction, 0 equals 5. If b is equal to 0, then we do still have only one solution, since there's a pivot still in every single column. If the columns are linearly dependent, then T is not 1 to 1. And that's when you have some free variables. And so the null space of T is not just the 0 vector, it's got more in it. And the nullity is not just 0, it's bigger than that. And that means that the rank has to be smaller than n, smaller than the number of columns. And that means you get infinity solutions. Whether if b is equal to 0, you get infinity solutions. And that includes the x equal to 0. If the rows are linearly independent, then T is onto still. And we did see an example of that in the last example. That would be that each row has a pivot. But that means that the rank would have to be equal to m, since there's m rows, and that would be the total number of pivots. And that would have to be smaller than n in order to make the rows linearly independent, but the column's linearly dependent. Then you get that infinity solutions, and if B is non-zero, you get X's in the span plus a specific solution. If both the columns and the rows are linearly dependent, then it's not onto, it's not one-to-one, nothing is true. The rank is smaller than M, but that's about all that we know. And it could be infinity solutions or no solution, depending on whether there's that row of zeros runs into a contradiction or not.